So in this video I will show you how to compute or how to apply the Black-Scholes equation to try to compute the price of an European call option. So let's begin. So we have here our exercise that says the following. So we want to compute the price of an European call option on a stock with a current price of $42. So the current stock price is $42. The strike price is $40. The expiration date T equals 6 months. And we already know that we always convert months to years. So this is half of a year, or 0.5. The risk-free rate is 10%. And the volatility, let's call it sigma, equals 20% per year. So given these data, they want us, or the exercise is asking us to find out the price of an European call option using Black-Scholes. So the first thing that one should write is precisely the call option, or the European call option formula for the Black-Scholes. So the European call option according to Black-Scholes formula. So this formula is given by, so the call, let's put here, the call equals the normal distribution of D1 associated with the stock price minus the normal distribution of D2 associated with the strike price discounted at the risk-free rate. And we also need to know what are the values of D1 and D2. So D1 is nothing more than the log normal assumption of the stock price, of the ratio of the stock price and the strike price, plus the drift of the stock, which is the risk-free rate, plus the volatility or the variance of the stock divided by 2, multiplied by the time period T. And all of this should be divided by the volatility square root time period. And in the same way, we can express D2 in terms of D1. So D2 equals D1 minus the volatility of the stock price square root of the time period. So how do we solve this? Well, the first thing to compute are precisely these values of D1 and D2. So let's start. So we just replace the values. So D1 is going to be again the logarithm of the current stock price, and I know that the current stock price is $42, divided by the strike price, which is $40, plus the risk-free rate, which is 10%, plus the variance, which is 0.2 squared divided by 2, multiplied by the time period, which is a half, or 0.5, divided by, again, the volatility multiplied by the square root of the time period. And if you do the calculations, this should give 0.7693. In the same way, if you compute D2, it's going to be, again, it's going to be expressed in terms of D1, so it's going to be the 0.7693 minus the 0.2 multiplied by the time period, 0.5. So D2 should be equal to 0.6278. So this is the easy part of the problem. Now we need to find out what are the values of n of d1 and n of d2. So n of d1 and n of d2 is nothing more than the probability distribution of these two values. And in order to do that, we will need the help of this probability table. So if such exercises appears, we would give you this table to compute the values of d1 and the normal distributions associated with d1 and d2. So how does this work? So we need to compute the values of n of d1 and n of d2. In other words, I want to know the value of n of 0.7693. And what is this equal to? Well, the trick is the following. You separate the number, you break this number into two, you grab the first half of it and you plug it in as the normal distribution of 0.76. Okay. And then you grab the second one, you grab the second half, and you plug it in as a scaling factor of 0.93. And all of this will be between an interval. So if we think about the number, let's just put it here. So if we think about the number 0.7693, we know that this number is in between some number 0.76 and another number let's put this in another color, 0.77. So 0.7693 falls in between a number which is 0.76 and another number 0.77. So when you try to, then we just put these values back in this expression. So it's going to be this one here in terms of its normal distribution, 0.77, minus this one here in terms of the normal distribution. So how do we find out the values of n? Well, for that I need to check my table. So n of 0.76, so let's go here. Again, we want to know n of 0.76. This means the following. It means that I will go here, so 0.70, let's put it in red, and I will walk, so 70, 71, 72, 73, 74, 75, 76. Okay, so this is n of 0.76 here. So it means that n of 0.76 is nothing more than this value, 0.7764. So let's plug in this number back into our calculations. So this is going to be 0.7764 plus the scaling factor 0.93 multiplied by the numbers in the interval, so the normal distribution of 0.77. So the normal distribution, now I want to know n of 0.77, and n of 0.77, it's again, I start in 0.7 and I will move forward until I find the other part, the 7. So it's going to be here. So it will be here. So again, 70, 71, 72, 73, 74, 75, 76, 77. So this is going to be equal to 0.7794. So I grab this value and I plug it in my calculation. So it's going to be 0.7794 minus the 0.76 that we already computed. So it's the 0.7764. So if we make the calculations, we will find out that n of 0.7693 equals to, this should be equal to 0.7792. So first one done. Now I need to do exactly the same thing, but for the value of D2, for this value here. So again, how do we do it? So it's exactly the same thing. I want to do the normal distribution of 0.6278. 78. So again, the trick is I break the number into two. I grab the first value and I put it as a normal distribution, 0.62. I grab the second value and I put it as the scaling factor. And then I put this in between an interval. Maybe I need to put some space, more space in this interval. Okay. So what is this interval again? The number 0.6278 falls in between 0.62 and 0.63. So in other words, this is going to be the normal distribution of 0.63 minus the normal distribution of 0.62. And again, I need to go to the table and check what are the values of these numbers. So n of 0.62. So now I want to find out n of 0.62. So again, I go to the table and I find out that 0.6 is here. So 0.60, 61, 62. Okay. So this is going to give 0.7324. And we also need to know the value of n of 0.63. So if this is 0.2, 0.63 is here. So it's going to be 0.7357. So I plug in these values back here. So this is going to be equal then to 0.7324 plus the scaling factor 0.78 multiplied by the upper bound on this interval, which is 0.7357 minus 0.7324. Okay, so if you do the calculations, this should give approximately 0.73, 7350. Okay, so we are not finished yet. So we just computed the values of n of D1 and n of D2. Now we need to compute the final price of my option. And again, so let's put here, okay. Let's put here compute option price. And this is nothing more than the application of the Black-Scholes formula. So the call option is again a normal distribution of D1 multiplied by the current stock price minus the normal distribution of D2 multiplied by the cash discounted, the risk-free rate. So if I just substitute the values, so I know that n of D1 is this one. So this is n of D1. And this one here is n of D2. So I just substitute the values. This is 0.7792 multiplied by the current stock price, which is here 42. So 42 minus the normal distribution of D2, that it's here, 0.7350 multiplied by the strike price, which is 40, and the exponential of minus the risk-free rate, which is 10%, and the time period is a half, 0.5, 6 months. So again, if you do the calculations, you will find out that the price of the option should be something close to $4.75. Okay. So this is how you would compute the Black-Scholes formula of a call option.